welcome back, everyone. So, welcome to end of week 6. Congratulations on nearly making it through 6/10 of the quarter. It's crazy. We only have 4 weeks left. Some quick reminders. We have the week 5 exercises due this Saturday. They should be very quick. They're really just intended to get you warmed up with multi-threading and using mutexes. So they shouldn't take you long. And we also have Project 1, the debugger assignment, due Tuesday. So if you haven't started that yet, please start like today, if possible, because it will take some time. But we are here to help, and if you run into any road bumps, just message us on Slack. We're happy to hop on a Zoom call or do whatever we can. We're also staying after class, so if you have questions on lecture material or on the assignment, please let us know, and we'd be happy to help. Also, Armin posted a quick poll on Slack. So we would like to have some event called Not Office Hours, where we just chat about whatever, maybe play some online multiplayer games. And yeah, I think it'll be a really fun time where we just get to know each other a little bit better, given that we haven't been able to meet in person this quarter. So if you're interested in that, please react to the messages on Slack to let us know when you can make it, and we'll announce that tonight. All right, so today we are talking about a concurrency primitive called channels. And in order to understand channels, you need to understand the context from which they come. Like you have to understand the motivation for this. And so we've been talking about multi-threading for 2 weeks, and you've been learning about primitives like mutexes and condition variables and semaphores in order to safely manage multi-threading. But let's take a step back and let's think about what are the basics that we're dealing with here? Why do we like multi-threading? What are some reasons that multi-threading is preferable? Anyone can shout some stuff out. That's true. Why do we like multi-threading over multi-processing? Multi-processing would also allow us to do something like that. Yeah, sharing data is easier. It's just generally easier to work with. And why else? It's faster, yeah. The context switching overhead is lower. So if you context switch between processes, you have to swap out the virtual address space, and that's more expensive. Whereas if you context switch threads, then you don't have to do that, and so it's cheaper. And also, as you mentioned, the communication is also a little bit cheaper. Writing into a pipe can be a bit slower than just writing to a memory value in the same memory address space. So those are some reasons that we like multi-threading. Why do we not like multi-threading? Why is multi-threading a huge pain sometimes? Yeah, really, it all comes down to we share memory. And because we share memory, we can have data races. Threads can screw up each other's virtual address spaces because it's all the same. They all share memory. And so that is really the root cause of all of our problems. And so let me make a radical proposition here. What if we tried to preserve the benefits of multi-threading, but we didn't share memory? And you're like, wait, Ryan, back the truck up. How is that supposed to work? Like, how are we supposed to have threads that work together when data is involved if they can't share memory? And there's another systems programming language called Go, which has become very popular in recent years, and it has a slogan that says, and I can't read it because Zoom is blocking it: "Do not communicate by sharing memory. Instead, share memory by communicating." And this is getting at an idea of message passing. Instead of having shared memory, you can exchange messages. So this is the communicating part. That contain information. You can put information inside of messages, and that's what they mean by share memory by communicating. Whatever data it is that you need to collaborate with different threads, you can put that inside of a message and send it to a different thread, so that you're sharing memory in that sense, by kind of copying things in between threads rather than having some shared area in memory where all of the threads are looking. Each thread has its own memory, and if it needs to share it, it sends a message to some other thread so that they can access whatever data it is that needs to be processed. And in that sense, you're not communicating by sharing memory, which is what we typically do in multi-threading world. You share memory by communicating. Bit of an interesting slogan. But it's one that has become very powerful in the last decade. And really the big point here is you can't have data races if there's no shared memory. Right? That's kind of what causes us so much pain in multi-threading land, is that we're trying to manage this shared memory, which has a lot of benefits, but also creates a lot of downsides. And if you don't share memory, well, you can't have data races. So this comes from a theory called communicating sequential processes. You have separate processes that are sequential. So sequential just means like you write some code and it executes in order. Easy peasy. We've been writing that since 106A. And because there's no shared state, there's no data races. These processes are isolated, and they communicate over these channels. This model, it's a theoretical model, but it serves as the basis for a lot of newer systems languages that have responded to the pain of race conditions over the last several decades. So you may or may not have heard of Go or Erlang, but they're two languages that really, really took this approach to heart and are totally designed around this idea where they don't really have mutexes. That's not entirely true. Go actually does provide mutexes, but the language itself is built around these processes or these threads, or they call them Go routines, that talk to each other not by sharing state, and not by using mutexes and condition variables, but by using channels. And actually, you may not know this, but this is actually where Rust started as well. In early Rust, there were no mutexes or condition variables. Rust used to be a lightweight task-based language, and channels used to be the only communication and synchronization primitive. You can get channels in other languages as well, and we'll talk about like what exactly these things are, so you have a better sense of what you're dealing with. All right, so I'm going to give you two frames of comparison for you to understand channels. And the first is, if you understand semaphores, you already understand channels. So to recap semaphores, the analogy that I always use to explain semaphores is semaphores are like a bucket of balls. Except you don't actually put real tangible things in the bucket. It's just a bucket of like stuff. Bucket of permission slips, as Jerry calls it, or a bucket of whatever it is. It's just a metaphorical bucket that you can put things in and take things out of. And semaphores are used for synchronization, not for communication. Because they don't carry data, you can't really communicate very much through them, but they are very useful for synchronization. You always have to pair them with an accompanied buffer or mutex if you want to use them for communication. So, say that you are trying to get some data from thread 1. We have a buffer and an associated mutex to prevent race conditions with that buffer. And then thread 1, anytime anything gets added to that buffer, thread 1 wants to take it out and do something with it. So the first thing thread 1 should do is wait to ensure that something is in the buffer. So thread 1 will wait on the semaphore. And if the semaphore is non-zero, meaning there is something in the bucket, thread 1 will go and grab it. And because it passes the semaphore.wait, it knows something is in the buffer. So it can lock the buffer, and then it can go and grab the thing out of the buffer. Something in the chat. Oh, the animations. Yeah, magic move in Keynote is awesome. Thank you for appreciating my stick figures. Then the thread can unlock the mutex because it no longer needs it. So it unlocks the mutex, and now it wants to pull something from the buffer again. So, but there's nothing in the buffer. So when it calls semaphore.wait again, it looks into the bucket and it's trying to take something out, but of course nothing is there. And so that thread blocks. If we now have another thread that comes along and wants to add something to the buffer, it first will acquire the lock. So it locks the lock. Then it puts something inside of the buffer because it has exclusive access to the buffer. And then it unlocks the lock. And now, to signal that something has been added to the buffer and wake up anybody who's waiting, it will call semaphore.signal. And so metaphorically, this is throwing a ball inside of the bucket. And thread 1 will then wake up from its semaphore.wait call. And now it knows that something is inside of the buffer. So it can lock the lock again, take the thing out, and lock the lock. Unlock the lock. Everyone make sense to everyone so far? This is just semaphores as we use them in 110. So channels are actually the same, except instead of being a metaphorical bucket, it actually has associated data storage. Instead of being a bucket of permission slips or a bucket of balls, it's a bucket of structs, of like whatever kind of struct that you want to put inside of it. And so if thread 1 wants to take things out of the bucket and process them, it calls... each channel has two ends. It has a receive end and a send end. So thread 1 takes the receive end and calls receive on it. And what that does is if there's something there, it just pulls it out and it returns it. So thread 1 will have access to this struct. And then if it wants to process something again, it can call receive end.receive again. And of course, if nothing is in there, then it will block until thread 2 comes along and calls send end.send, and that will place something inside of the bucket, and that will wake up thread 1, which will receive that struct inside of another variable. Does this make sense to people so far? Thumbs up, thumbs down. Repeat the function call that sends the data. Yeah, so it's just .send. And I'll give you a code example that will put everything into context, but I want you to understand conceptually what's happening here. It's just a semaphore, except instead of also needing an accompanying mutex and buffer, you just have this one communication primitive. You put things inside of the channel, and you can take things out of the channel, and if you try to take something out of the channel and there's nothing there, then you'll wait for something to be added. Also, in this example, I've shown a bucket with only one thing at a time, but you can have as many things as you want inside of a channel. Thread 2 could add 5 things before thread 1 takes anything out, and that would be fine. Then the channel has 5 things in it, and thread 1 could call receive 5 times without blocking. The 6th time it calls, it'll block because nothing is in the channel. That's a really good question. Like, what is actually used under the hood? It depends on the implementation, and I'll talk a little bit about implementation in a few slides. In many cases, it's a linked list. Or a linked queue, really, like a doubly linked list. Okay, so then thread 1 can take the thing out. Okay, cool. So the other comparison that you can make here is channels are really like pipes from multiprocessing land with 2 differences. They're really fast. So in a pipe, anytime you want to write to a pipe, you have to use the write syscall, and every time you want to get something out of a pipe, you have to use the read syscall. You may not realize this, but syscalls are actually very slow compared to normal function calls. And the reason for that is they have to make a context switch into the operating system. So the processor is operating at an unprivileged level, usually. And then whenever you make a syscall, the processor has to switch into privileged mode where it can access any memory address and do a bunch of things that normal processes are not allowed to do. So using pipes is not slow compared to some other things that you might want to do, like writing to disk or reading from a network. But compared to making function calls, it is quite slow. Also, channels don't exchange a stream of bytes. You could use them to exchange a stream of bytes if you wanted to, but you could also just put structs inside of them. They're strongly typed, which is extremely nice for using them, because instead of having to, like, if you want to send a number, for example, instead of having to convert the number to a string and send it in, and then when you receive it, deserialize it back to a number, you don't have to do any of that. You just put the structs in, the types in, whatever data you want into the channel, and then you get it out, and it's the same type. And if you think back to this Chrome architecture diagram that we saw last week, it has this thing in here called a channel and this IPC. And what this diagram is getting at is it has this notion of inter-process communication channels. Channels are just pipes, but in the context of multiprocessing, they're just pipes, but with an extra layer of abstraction to serialize and deserialize objects into bytes. So that when you send something into this IPC channel, it gets converted into a string of bytes that can be written into the pipe. And then when you read something out of the pipe, it converts that string of bytes into an object that is usable by this application. When we're talking about channels in a multi-threading context, this serialization and deserialization doesn't happen. We want them to be as fast as possible, and so they're not the same as multi-processing channels, but it's the same idea. Channels are very much like pipes, but they're simpler to use and they're faster. Make sense? All right. So how do we actually use channels? And the first thing that you should be asking yourself is, I kind of see where you're going with this, and it seems like it might be useful, but isn't it bad for performance if we're not sharing memory? Like, part of the reason that we wanted to use threads was because it's easy, because we're sharing memory, and it's also faster than multiprocessing. And it seems like we're kind of throwing out that faster advantage if we have to pass messages. Can somebody explain why message passing might be bad for performance? Just like in a sentence. I kind of just alluded to it. But I want to make sure everyone's on the same page about why this should be concerning. That's true. So if we're talking about multi-threading, well, threads already share memory, and it's redundant to pass a message. That's true, but redundancy might not necessarily be bad. If that redundancy can prevent us from making safety errors, then that's probably worthwhile. But there's something else here, and I think you're on the right track. That redundancy is bad. Why is it bad? It's more than just like redundancy. You'd put a lock around shared memory. Okay, so what would be the memory that you would put the lock around? Would it be the objects that you put inside of the channel? Mm-hmm. So that's true. It does need to be shared it does need to be stored in the process's memory. But how would you, if you had to design this yourself? Actually, let's talk about this. I'm going to talk about it later in the slides, but we should talk about it now. If you were to implement this thing, how would you implement it? Like, yes, this struct needs to be stored somewhere in memory, but where would you put that lock? So it would need to be on the heap. But the problem is that if I'm trying to think of a way to explain why it's difficult to put locks around arbitrary data. Usually when you're writing a program and you're using locks, you know what data you have and you have multiple threads trying to access that same data at the same time. Like you have a global variable somewhere, or some variable that gets shared between threads. All the threads know what that variable is, and they know exactly where the variable is, and they know that there's a lock protecting that variable. And so before touching the variable, they acquire the lock, then they touch the variable. But in this case, thread 1 is just being handed things by some number of other threads. In this diagram, I've only drawn one other thread that is handing it things, but we could imagine that there are 5 different threads that are producing work that needs to be processed, or producing structs that need to be looked at for whatever reason, and they're just handing it to thread 1. And so in the code for thread 1, we don't really know. It's not like there are 5 different variables somewhere that we can look at and we're like, okay, I need to fetch from these 5 variables. It's just there's this incoming data stream that thread 1 is receiving, and thread 1 doesn't know how many structs are going to come out of this channel. It's just repeatedly like trying to pull something out and then looking at it, trying to pull something out and looking at it, trying to pull something out and looking at it. And so using locks on the individual data doesn't make as much sense here, because there is no central place where we're looking for that data, if that makes sense, because we don't even know how many pieces of data, how many structs we would need to look at. We don't know like how many variables there are, and so does that make sense at all?
I think it might be helpful to think about like last lecture, the thing that we implemented at the end, like the summa plus plus is like very similar, right? Like you're taking these messages and you're putting them somewhere, and then you're just pulling them out of some structure. So it's like they don't live like all in a centralized place. You're taking them, you're queuing them up, and then you're providing them to some sort of receiver that's going to take them off that queue. Does that make more sense? Or
and actually, I think the summa plus plus thing may be a little confusing for this context that I'm trying to give. But if we go back to the motivation for channels, so it was in this this slide. What we're trying to do is we're trying to avoid race conditions. But instead of doing it by using locks, so normally race conditions happen because you have some variable that is shared between threads, and then multiple threads are trying to access that memory at the same time. What we're trying to do here is we're trying to create a totally different paradigm of doing multi-threading. And we're saying we're not going to share memory at all. If you want 2 threads to communicate, they're not going to go look at some shared data structure that has a lock on it or something like that. There's going to be no variables that are shared between threads, no globals, nothing. Every thread has separate memory, and if they need to talk to each other, then they're going to pass messages to each other. So thread 1 is going to like put something in an envelope and throw it at thread 2. Thread 2 is going to receive it, and it's going to be like, oh, I have this data now. Now I can use it. So that should feel expensive. Like detach yourself from everything you know about multi-threading right now, and just think about this as a thought experiment. Because it turns out that in practice, this is not actually what we do. But I want you to understand why that is, why it is that we don't follow this ideal theoretical model. I mean, this is a theory from 1978. It's been around for a long time. And it's well appreciated that if you follow this model, you won't have data races because you don't share data. If you want to pass data around, you pass it in these messages. But why is that expensive? That's partially true. So you said anytime they need data, they need to like read or write it. So the threads do have their own memory. It's just that they aren't sharing memory with other threads. And so really the problem that I'm trying to get at here is if you have data that you want multiple threads to be working on, they all need to have their own separate copies of that data. They don't share memory. Therefore, if you have some data that all the threads need to work with, they all need to have their own separate copies of that data. And if you say you have like a vector of gigantic strings, and you're trying to take that vector of gigantic strings and you're trying to share it with another thread, you're trying to send it over to another thread. If you want to put that in an envelope, you better find a really fat envelope, because you're going to need it in order to send that huge vector of a ton of really long strings. And then you have to send that to this other process, and that is really expensive. There's a lot of overhead associated with copying here. If you want to have each thread have its own copy of data, that's great. You're not going to have data races. They're not sharing memory. But now you have to deal with this overhead of copying data here, copying data there, copying data here, and all of this replication of data in a lot of places. That is what strikes me as being problematic about this approach. Is now you have a bunch of copies everywhere, and copying memory is not cheap, especially if it's really big. If you're just sending a number, it doesn't really matter. But if you're trying to send over a vector of strings, now you're going to have to copy that to another thread. And what if you're just trying to move it to another thread? Like, what if you're trying to send a vector of strings to another thread and you're not going to use it after that? Really, it would be nice if you could just say, oh, here's a pointer to this region of memory. But if you're not sharing memory, then you can't do that. You have to copy it over, even though you're about to discard your own copy. Does this make sense, what the problem is? So what do we actually do? And oh boy, I'm going to have to go through all my animations again. This is fun. All right. So what do we actually do? And the key here is that when we talk about channels, almost always, this may not be true in some programming languages, but in all the ones that I know of, they don't actually follow the theory of communicating sequential processes. That theory says that all the processes, they call them processes, but you call them whatever you want. Some languages call them threads, some languages call them Go routines, some call them tasks. It's the same idea. That theory says that they should not share memory, and they should communicate exclusively by using channels. And actually, that's not what happens. We share some memory. So we do share the heap. And when we put information into channels, we make a shallow copy of that data. So we are doing some copying, but it's only a shallow copying. We're not copying all of the data here. And to help you visualize this, let's say that we're trying to pass a vector of, in this case, numbers, but it could be a vector of really huge strings. Let's say we're trying to pass a vector from one thread to another. So when we put this in the channel, really, according to channels theory, we should be copying the entire vector. We should be doing a deep copy of this whole vector and putting it inside of the channel, copying it somewhere where the other thread can receive it. But that's not what we do. We do make a copy, but it's a shallow copy of the vector struct. And that vector struct contains a pointer to the heap where the actual data resides. So this isn't a very expensive copy. This is a pretty small struct. I'm sure Vec has more fields in it than this, but the way that I've drawn it, this is just two numbers and a pointer. Let's assume that the numbers and the pointer are the same size. So this would be 24 bytes. That's not a big deal to copy, especially if that vector is really huge. And then thread 1 copies it into its stack. But that's also okay. It's really not a big deal because we're only doing a shallow copy here. We are sharing memory to the heap, but we're going to say that's a trade-off we're going to make, because we don't want to have to copy huge amounts of memory every time we want to send in something into the channel. So you might say, like, hey, that seems problematic. The whole reason we're talking about this is because channels are supposed to be able to be another model for safety. If we use channels, then we can't have data races, right? And the only reason that this works is because the threads aren't sharing memory. Now you're telling me that they're sharing memory. What's going on here? And actually, that's true. And in Go, for example, you can still have data races. The channel model, as implemented in practice, fails to prevent data races. If you pass a pointer into a channel, which you are doing when you pass a vector, if you pass a pointer into a channel, now you have you can potentially have multiple pointers to the same data. because you're copying that pointer into the channel and then you're copying it out. Now you have multiple copies of a pointer to the same location in memory. If you had copied the entire vector, it would be fine that you have two vectors on both ends because they're deep copies of each other and they're separate. But if you copy just the vector struct and it's pointing to the same region of in the heap, now you have two pointers to the same region of memory and you can still have data races. And I've read horror stories of application developers trying to debug things because they passed something into a channel and then they accidentally used it again after that. And the language doesn't prevent you from doing that. But as you might imagine, Rust's ownership model does not allow you to do that. When you send something to a channel, ownership of that value gets transferred to the channel. So you can't use it after that. And say that you pass a vec into a channel, what it's doing is it's taking ownership of the vec struct, so you can't use it after that. But it's not doing a deep copy. It's not copying all of the data. It's only copying just those 24 bytes of the struct itself. Does this make sense to people? Thumbs up, thumbs down. Any questions? All right. So I'm going to give a code example of how to actually use this, but before I do that, I need to talk about the API. And this is a little bit of a sad conversation because this is one place where Rust actually does not shine at the moment. So the ideal channel is what we call an MPMC channel. That stands for multi-producer, multi-consumer. That means that you can have multiple threads sending to the channel at the same time. And you can also have multiple threads receiving from the channel at the same time. So a pipe in multiprocessing is multi-producer, multi-consumer, because you can dupe a file descriptor to multiple processes. You can dupe the write end to multiple processes. You can dupe the read end to multiple processes. You can do whatever you want. And this is the ideal channel because it gives you the most flexibility. You can do whatever you want with it. If you only want to have one thread sending and one thread receiving, that's fine too. But you have the option to have multiple threads sending or multiple threads receiving at the same time. It turns out that you actually already know how this works because you implemented this on Tuesday. Armin walked through the implementation of, we called it Sema++ back then, but really that was a channel. And if you think about the semaphore channel stick figure thing, that's basically what we implemented. It's just a simple mutex with a vecdec, which is just a queue, and a condition variable to wake threads up when things get added and whatnot. So this seems really easy to implement. So why are we talking about this in the first place? Like, why aren't all channels MPMC? And the reason is that it has to do with performance. Why might this approach not give us the performance that we want? Does anyone have any guesses? So you have to lock a mutex before touching the queue, and therefore only one thread can touch the queue at a time. That is true. That is what gives us safety. So that is preventing race conditions in the channel implementation. Why is that potentially a bad thing? You're right, by the way. Interesting. So it's not multi-producer, multi-consumer in the sense that you can't really have multiple threads writing at the same time. That is true. You could make that argument. But then I'm not sure if you ever can have, I think by that definition, I'm not sure if you ever can have a real multi-producer, multi-consumer queue. Because if there is one queue, if two threads were to be able to add to the queue at the exact same time, I'm not sure. Maybe it is theoretically possible to have some queue. Yeah, maybe it is possible to have a theoretical model where like two threads can add at the exact same time, but I haven't heard of anything like that in practice, just because the queue has to exist somewhere physically in memory, and you'd have to come up with a really clever solution to allow two threads to modify it in such a way that when they're modifying at the same time, the end result is coherent and includes both of the things that they added. So we actually we're okay with having one thread writing at any particular instant, but a mutex is still something that we would like to avoid. So there's two parts to this. The first part is, okay, we don't want to have multiple writers at the same time. But what if one thread is adding to the queue and one thread is removing from the queue at the same time? Should we allow that? So it does seem like in theory there should be some ways to do something like that. And I mentioned that channels are often implemented as a linked list, and that's one of the reasons why, because if you're modifying the two ends of the queue, as long as you're not modifying the same thing at the same time, then we might be able to come up with a solution. And it seems like there should be some way to allow one thread to be pushing onto the queue and one thread to be popping from the queue at the same time. That will improve performance, because if you have a thread that is adding a ton of things to the queue in rapid succession, like very, very quickly, you also want it to be able to pop things off the queue as fast as possible. And those two operations don't necessarily have to conflict with each other. So that might be something that we want to allow. And a mutex won't allow that because both of those operations are modifying the queue. And with a mutex, you can't do that. Another thing is that mutexes are actually, they're not cheap. Because say that you try to acquire a lock. First of all, a mutex involves a system call. And we already mentioned that we want to avoid system calls if possible. So mutexes are already expensive off the bat, regardless of how they're implemented. And the way that they're implemented is, say that you want to touch the queue, but somebody already holds the lock. If that happens, you're actually taken off the processor, and you get added to the queue of processes, and you don't get to run again until you get scheduled to the processor again. So a typical time slice on a CPU might be something like 10 milliseconds. If you're at the very beginning of your time slice and you get booted off the CPU, you don't get the rest of your 10 milliseconds. Even if you only used 100 nanoseconds, you've lost the rest of your time slice purely because you attempted to acquire a mutex and it was already locked. And furthermore, you're going to get booted to the bottom of the queue until you get your processor time again. And so it might be a significant amount of time before you get scheduled on the CPU again. And if these queue operations, these queue and dequeue operations are really, really, really fast, like if this takes on the order of 50 nanoseconds to add something to the queue or to remove something from the queue, it would be ideal if we didn't give up our time slice just because somebody is currently modifying the queue. It would be better if we could stay on the processor busy waiting. We mentioned one time that busy waiting is usually bad, but there are certain really high performance situations where busy waiting is actually a good thing, because you don't want to give up your time slice and let other processes run, because you know that I just need to wait like 50 more nanoseconds. I really don't have to wait that long. Just give me 50 more nanoseconds and I'll be fine. Please don't take me off the processor, because I'll be ready in just a moment. And so if we want a fast implementation, we can't use locks. And this is very, very, very difficult to implement well. Go's channels are MPMC, but they're known for being slow because they basically do a mutex vecdec. They just, instead of using a mutex, they use a futex, they're called, which is a fast user space mutex. So it avoids the system call part, but it doesn't avoid the locking part. and Go's channels are slow for that reason.
Oh, Ryan,
Rust,
sorry, there's a question from Hannah in the chat, and I just wanted to confirm
sure.
here. So,
Uh, my Zoom is not. I think you're muted. I still can't hear you.
the question is there an issue if the queue only has one element or if it's empty? Because earlier you were mentioning that how you could like simultaneously pop and push, and presumably if
Yeah,
it just has one element, you need to synchronize access to that.
for sure. There are a lot of edge cases that you have to worry about, and those are just more examples of why it's so difficult to implement this without a mutex. It's really hard to get this right. But Rust said we need to get this right. We really don't want a slow channel because, especially at the beginning when channels were the only option available, they needed to be fast. And so Rust does not have an MPMC channel. Rust's channel is actually an MPSC channel, single consumer. And that's not ideal. So it's great if you want to have, if you want to aggregate results of an operation. It's also great if you just have two threads that are talking to each other. But it doesn't really work so well if you need to broadcast messages or distribute messages. For example, like if you want to have a work queue where you have a bunch of stuff in the queue and a bunch of workers take stuff off the queue and process them. Also, because this is one of Rust's earliest APIs, there is a lot of inconsistent terminology and places where things are not so intuitive. There's a really good article that I linked here that talks about this is one of the core Rust developers saying we need to overhaul channels. And there's a pretty good chance that within a year or two, the Rust channels standard library implementation will be replaced. They're either going to keep the API and replace the implementation, or they're going to deprecate it entirely and introduce a different API. They definitely will keep channels because they view this as a very important feature in modern concurrency, but they acknowledge that there's issues with the standard library channel, and they're going to replace it. What are they going to replace it with? There's a crate called Crossbeam, which is maintained by this core Rust developer. Basically, what he did with this Crossbeam implementation is he said, if we were to redo Rust channels from scratch, how would they look? If we didn't have any historical legacy that we were trying to uphold, and we were to do it from scratch, how would they look? So he redid the API, and the implementation is extremely fast. It's mostly lock-free, and it's even faster than the existing MPSC channels that Rust has. So he went through a lot of iterations, and it took a really long time to develop, but this works. And if you're interested in the implementation, there's a really good read that is linked here. So in this code, I'm going to be talking about Crossbeam channels, not standard library channels. And if you use channels in your code, it's a good idea to use this library instead of the standard library one, because this is the officially recommended one for now, and very soon the standard library channel may change. And by the way, if you want to use channels in other languages, I mentioned this earlier, but channels are not specific to Rust. They're a really good idea in general. And if you want to use them in other languages, there are libraries. For example, like Boost provides channels for C++. And so you can check those out. All right, so in the remaining 4 minutes, I'm going to talk through how you actually use these things. So you call Crossbeam channel unbounded to create an unbounded channel. And unbounded means that there's no fixed capacity of the channel. It's just a queue with an unlimited buffer size. You can add things in until you run out of memory. And this returns you two objects, a sender object and a receiver object, or a sender struct and a receiver struct. Those are really handles to the underlying channel. And they're managed so that the underlying channel struct has a reference count of how many senders and how many receivers are active. It's really similar to RC and ARC in this regard. Like when you clone an RC or an ARC, it increments some internal reference count. That's sort of similar to what is happening here. So it returns these two ends of the channel. And what we're going to do, also, I should mention, I got ahead of myself. What we're doing here is we're just re-implementing farm again for the third time. So in the week 5 exercises, you re-implemented farm, which was like a more basic version of farm that doesn't support receiving numbers via standard in. So that version took all the numbers to factor in argv so that they were all present up front and you didn't get any numbers added later on. And that really simplified things quite a bit. This version is going to be the full-fledged version of farm. It receives numbers via standard in. You can type numbers at any point. You can type in a bunch of numbers. It can finish factoring everything, and then you can type more numbers, and it will factor those numbers as well. So we'll spawn a bunch of threads identical to the number of CPUs that we have, and then we'll call receiver.clone. And what that does is it creates, it just clones the receiver struct. It's not actually cloning the channel. And this is doing a trick similar to RC, where it's really, I didn't update the reference count here, I should have, but it's really just incrementing the reference count in the underlying channel struct. Then what we'll do is we'll spawn our thread, and our thread is just going to loop. So while it continues to get numbers out of the channel, it will try to factor them. So two things happening in this code here that I want to highlight. First of all, this move is going to move any referenced variables into the thread stack. And so we're using this receiver variable here. And so what that's going to do is it's going to move receiver into thread 2's stack. So now the thread 2 has that. And also this like while let OK thingy you may not have seen before. All that is doing is it's saying while receiver.receive returns the OK enum, unwrap the OK enum into this variable called nextNum. So it's going to basically unwrap the return value of receiver.receive. And then once receiver.receive returns error, it's not going to panic, it's just going to break out of the loop. So this is saying read until receive returns error. And when does receive return error? Receive returns error when the channel is closed. So when there are no more senders to the channel and you try to receive from that channel, that's when receive will return error. It's kind of like calling the read syscall on a pipe. Read doesn't return an error, but it returns 0 to indicate that you've reached the end of the file. That's kind of what's happening here. It's returning error to indicate that you've reached end of file in the sense that no more data is coming because there are no senders here. Then our program, the main thread, is going to read from standard in. And so it's going to try to repeatedly read a line from standard in and parse that as a number. And then it is going to write that to the channel. So it's going to send the number to the channel. Likewise, send also returns a result. And it just returns an error if there are no receivers. If you're trying to send to a channel where there are no receivers, that seems suspicious. That's probably a mistake. And so it returns an error to indicate that, hey, you're trying to send to a channel where nobody's listening. That's probably not good. And in this case, that definitely should not happen. If that happens, something's terribly wrong with our program. And so that's what I called expect here, saying just panic if that happens. Then what we do is after we have written some numbers, we drop the sender. So this is something you may not have seen before, because usually when a variable goes out of scope, it gets automatically dropped, and that's how we've been dropping our variables. But Rust has an option to drop early if you want to. It's basically calling free on the memory, except the compiler is smarter than that, and it ensures that you can't have use after freeze, and it also ensures that there are no double frees or anything like that. So if you want to drop the sender early, you can call drop sender, effectively like kind of kicking it out of scope, and that will remove that from the sender stack. So now there are no senders, which means that the channel is closed. So any workers that are in that while loop that are trying to read from this channel, receiver.receive is going to return an error. So they'll break out of their while loop, and that will be the end of those worker threads. So the last thing that we do here is we join all of the threads to make sure that they exited successfully and did not panic, and to free up any resources. So that was a whole lot in 6 minutes. Apologies for going over. In a moment, we can stay after and I'll answer any questions. But I just wanted to conclude by saying you should pick the right tool for the job. Channels, I love channels. They work really great. They're such a simple and elegant interface. And in many cases, you can get by without using any mutexes or condition variables. They're much simpler to use. And even in Rust, I think Rust does an amazing job with mutexes. But even in Rust, you can still have issues if you lock or unlock at the wrong time. So as a quick example, if you're implementing a semaphore and you cv.wait to ensure that the counter is greater than 0, but then you unlock and relock before decrementing the counter, it's possible for some other thread to get in at that moment, decrement the counter to 0, and then you try to decrement the counter, and it's already 0, and so we end up with an issue there. The compiler doesn't complain because you're holding the lock whenever you're touching the variable, but that's still a problem. And in general, when you're using channels, it's just easier to reason about, and you don't have these sorts of issues. But channels have their own issues. And I mentioned Rust started out with channels, and they added mutexes. Why did they add mutexes? Well, channels don't always work, particularly when you have global variables. So if you have a global cache that you want all the threads to share, or if you have a global counter, think like ticket sellers, for example, it's very difficult because you have to replicate that state across all of the threads. And that's very hard to do well. So if you're using this kind of scenario where you have a global value that you need to maintain, then channels probably aren't the best choice. That's all I have for today. Thanks for coming, and please stay after if you have any questions about that code example, or about the assignment or whatnot. And we'll see you next week.